right, so we'll say a little bit more about directional derivatives, and in particular this special vector gradient vector. So this is the vector of partial derivatives of our function. Okay. This upside down triangle thing. Okay. Different people pronounce it different ways. Again, we're still solidifying the notation. Different academic fields have different ways of talking about this. So you'll see this pronounced either so if I were to read this out loud, I would say grad f of AB. The upside down triangle can be pronounced grad. And I guess that's standing in place of gradient. It can also be pronounced nabla. Why? I have no idea. So, an engineer or a physicist might say nabla of f of AB. I don't know why, but that's how they'd say it. So I usually pronounce it as grad f. Okay, this records the partial derivatives of our function. So the key fact, the thing that makes the gradient so important, is that the directional derivative in direction v is grad f dot v. Okay, so the gradient is sort of this naturally occurring thing when you look at directional derivatives. Another key fact that comes out of this formula so if you take the direction corresponding to the gradient, that direction is going to make this, wait, is that true? Yeah. And this guy is maximized. Okay, the direction of fastest ascent of a function is when you're dotting this thing against itself, basically. The biggest this will get is when you travel in the direction of the gradient. So this is not like a super duper deep calculus fact. This is just a property of the dot product, that the biggest A dot B can be is when you've got A dot A. And so something that comes out of it, but the direction of fastest ascent is the gradient. Does anyone like hiking? Anyone like hiking at all? Yeah, hiking's pretty good, right? Yeah. Tonight I'm going to Denver, so I'm really excited to go hiking kind of like in the desert and up like mesas and stuff. I'm super duper stoked for that. The gradient vector when you're hiking is the hardest direction to travel. Okay? The easiest direction to travel is negative gradient. Negative gradient is the direction that water goes. But if you really want to sweat and you're hiking, you travel in this direction. Okay. So that's a little bit about that. So one of the things about multivariable calculus is we have directions of fastest increase, right? In single variable calculus, we just have increase or decrease. But here we've got a choice of directions, and we can say which one is the one that's going up fastest. Yes?
So if the gradient vector is like uses directional derivatives, where's the formula?
Sorry, come again?
Does the gradient vector use directional derivatives?
No.
Oh, it uses
just the function. It takes the function at a point and gives you a vector.
Okay.
So the connection. Right. Okay. So the connection between gradient and directional derivative is this dot v. The gradient is something that you can calculate just on its own.
Just from partial.
Yeah, it's just partial derivative information. Yep.
And then is the vector that you get from a gradient, is that directional?
No. So, okay, well, yes. So we'll do an example that'll show why it's not itself a direction vector and that you need to normalize it. Okay. Questions are so good. Excellent. Okay, so if we are an ant and we are living on this parabola and we are going for a hike, then we're doing weird stuff in math class. But if we live on this paraboloid and we're standing at this point, what's the hardest direction to get out of? What's the steepest ascent? Right? So we will calculate the gradient. Okay, so take the derivative in each direction. So 2x, 2y. Okay. And now this thing, the gradient, is not a direction vector. Right? This thing has some length. Right? It's not a unit vector. So now we calculate the direction of steepest descent. Okay. Make a little note of that. not a direction vector. Okay. So we need to normalize down to length 1. So we divide out by the length of the gradient. So we use Pythagoras to get the length. That's a number, 1 over 2 root 2. Okay, now everything cancels. Direction we are traveling before is the hardest direction to climb. This is the direction of fastest ascent. The direction that we were picking, we noted that the derivative in this direction is bigger than the derivative in the x direction, bigger than the derivative in the y direction. In fact, it's bigger than the derivative in any other direction. Right? This is the unique maximal derivative. It's the direction that would be the hardest to climb. Okay. Would people like another example of that type? Okay, sweet. So yeah, we've got this. Okay. So we'll do one example of finding a rate of change going from one point to another point. One of the things that we can use this for is we can look at rates of change as we travel from one point to another point. Right? This information here implicitly specifies a direction. This is one of these places where we come up against geometric vectors versus algebraic vectors. We gotta think, should we plug in 3, 4, or the origin, or what? Right? Like, we've got two vectors here. Which one's the right one to care about? So there's our point 3, 4, and we want to go from this point to the origin. Okay, now that's not a unit vector, right? It's quite long. It's got length 5. So we have to normalize it down to a unit vector. So we'll make a geometric vector out of it. From this point to this point, we take the head, subtract the tail. Unit vector like this. Now we need a gradient.